Namaskar, hello, and a very warm welcome to this special webinar series, Listening to Learn. My name is Tanvi Khurana, and as you all know that this is the 39th episode we are here with. And as always, we discuss one of the topics related to science, and we of course have a guest with us in our studio. But before that, let me tell you our today's topic, that is wind tunnels and their applications. And जिसे हम हिंदी में कहेंगे पवन सुरंगें और उसके अनुप्रयोग. और आज हमारे स्टूडियो में कौन मौजूद है इसका आपका परिचय थोड़ी देर में कराएंगे, पर अगर आपके पास कोई भी सवाल है, आप कुछ पूछना चाहते हैं विंड टनल से जुड़ा हुआ, तो हम तक जरूर पहुंचाइए. आप हमें फोन कर सकते हैं. हमारा नंबर है 8800440559. अगर आप हमें इस वक्त लाइव देख रहे हैं NCERT ऑफिशियल हमारे YouTube चैनल पर, तो हम तक जरूर पहुंचिए. अपने सवाल लाइव चैट बॉक्स में लिखिए और हमें भेज दीजिए. 11 बजे तक हमारे मेहमान हमारे साथ मौजूद रहेंगे, आपकी सभी बातें सुनेंगे, आपके जवाब देंगे, आपके सवालों के जवाब देंगे, और बहुत ही इंटरेस्टिंग होने वाला है ये आज का सेशन. क्यों जानते हैं? विंड टनल्स आखिर होती क्या है? ये एक लार्ज ट्यूब्स होती हैं जो कि सिर्फ रिसर्चर्स ही नहीं, ऑटोमोबाइल इंडस्ट्री में भी इस्तेमाल होते हैं, एयरक्राफ्ट में यूज होते हैं, बाइसिकल, मोटर बाइक्स, जो गाड़ियां हम चलाते हैं आमतौर पर उस पे भी इस्तेमाल होते हैं. पर इसमें और क्या खास है? नासा क्यों इस्तेमाल करता है इसे? कहाँ इस्तेमाल करता है? बहुत कुछ है इसके बारे में जानने के लिए और इसके एप्लीकेशंस के बारे में भी जानने के लिए. इसके लिए हम आपको मिलवाते हैं हमारे आज के खास मेहमान से, पर उससे पहले हम आपको मिलवाएंगे हमारे आज के मॉडरेटर से, जो कि आप सभी जानते ही हैं, डॉक्टर गगन गुप्ता. स्वागत है सर आपका.
नमस्कार तन्वी.
नमस्कार सर. सर हैं DESM NCERT से, और DESM को सारा क्रेडिट जाता है, डिपार्टमेंट ऑफ एजुकेशन इन साइंस एंड मैथमेटिक्स को पूरा क्रेडिट जाता है इस प्रोग्राम को ऑर्गेनाइज करने का, इम्प्लीमेंट करने का और कंसेप्चुलाइज करने का. जैसा कि मैंने पहले भी कहा, अगर आपके पास कोई भी सवाल है तो बहुत सारे माध्यम हैं जिसके जरिए आप हम तक पहुंच सकते हैं. आप हमें इस वक्त PM विद्या चैनल नंबर 9, 10, 11 और 12 पर भी देख रहे हैं. लिसनिंग टू लर्न एक ऐसा वेबिनार सीरीज है जो एक आउटरीच प्रोग्राम है इंडियन डायस्पोरा के लिए. दुनिया में आप कहीं पे भी बैठे हैं, आप इस कार्यक्रम को देख सकते हैं, इसमें पार्टिसिपेट कर सकते हैं और बहुत सारी बातचीत भी कर सकते हैं. तो चलिए साइंस के कार्यक्रम को शुरू करते हैं, और सबसे पहले आपका परिचय हम सर से करवाना चाहेंगे, और उसके लिए हम रिक्वेस्ट करेंगे हमारे मॉडरेटर डॉक्टर गगन गुप्ता से. सर.
धन्यवाद तन्वी जी. सादर प्रणाम दोस्तों. आज का प्रोग्राम लिसनिंग टू लर्न, सुने और सीखे श्रृंखला का 39वां चरण है, 39th सेशन है. इस सीरीज को हमने अगस्त 2021 से शुरू किया था और लगभग एक बरस हम पूरा कर चुके हैं. और आज का जो मेरे साथ है स्टूडियो में, NCERT के स्टूडियो में मेरे साथ एक यंग मैन डॉक्टर प्रियांक कुमार फ्रॉम द बिरला इंस्टीट्यूट ऑफ टेक्नोलॉजी मेसरा रांची आज हमारे साथ है. ये इंस्टीट्यूट मेरा अपना इंस्टीट्यूट है. मैंने इस इंस्टीट्यूट में 3 साल रहा हूँ, और जिस डिपार्टमेंट से डॉक्टर प्रियांक यहाँ पर हैं, डिपार्टमेंट ऑफ स्पेस इंजीनियरिंग एंड रॉकेटरी, इट्स अ वेरी इंपॉर्टेंट डिपार्टमेंट इन द हिस्ट्री ऑफ इंडियन सिविलाइजेशन एंड इंडियन पॉलिटिक्स. दोस्तों, मैं आपको याद बताऊं कि 1971 की लड़ाई में, जब बांग्लादेश लड़ाई हुई थी, तब आपके विभाग में बने हुए रॉकेट्स डायरेक्टली वार फील्ड में यूज हुए थे. 1971 में सीधे इंडस्ट्री, सीधे स्कूल, कॉलेज, इंस्टीट्यूशन, लेबोरेटरी से सीधे वार फील्ड में रॉकेट्स यूज हुए थे. दैट्स अ वेरी इंपॉर्टेंट milestone with the Birla Institute of Technology, Mesra Ranchi, and to all you know that this is the institute which is still doing high quality research work and high quality teaching in all areas of engineering, science and technology. Before I introduce Dr. Priyank with all of you, let me just make a little preamble to today's talk. This is related with the fluid dynamics. Friends, fluids are the materials which can flow. Means we can have a liquid, a fluid, a gas is a fluid, a plasma is a fluid. So the category of these materials which can flow on its own are known as fluids, and the motion of those fluids is studied under fluid dynamics. In order to understand the properties of the materials and the gadgets and the automobiles, maybe in aviation industry or on the road industry, roads, transports, etc., all are being tested through wind tunnels. About this, all these testing mechanisms, Dr. Priyank will tell us more about it, all those things today. We will be learning all those things. Before Dr. Priyank start, let me give my credits officially to, we have taken some slides from the YouTube open sources, we have taken some slides from the open sources of National Aeronautical Bangalore websites, Google Images, and ANSYS web software systems. We thank all of them, and we have used their open source images in this today's session. So friends, Dr. Priyank Kumar is a native of Begusarai, Bihar, is presently working with the Department of Space Engineering and Rocketry, Birla Institute of Technology, Mesra, Ranchi. Dr. Priyank Kumar completed his bachelor's in mechanical engineering from the Maland College of Engineering, Hassan, which is an affiliated college with the Vishwesvaraya Technological University, Karnataka. Dr. Priyank completed his master's and doctoral programs in experimental aerodynamics in aerospace from the Birla Institute of Technology, Mesra, Ranchi, where he has been working for a long now. Dr. Priyank has experience of more than 14 years of teaching and research. He has published 18 articles in peer-reviewed journals of international repute and more than 50 deliberations and participations in national and international conferences in India and outside. Friends, Ranchi being the capital city of Jharkhand, which is an industrial and educational city of Jharkhand, Dr. Priyank is also associated with the Jharkhand government and its initiatives in higher education. Dr. Priyank is also handling industrial consultancy projects at the Birla Institute of Technology, Mesra, Ranchi. Dr. Priyank has handled 10 research projects sponsored by different funding agencies of the country. Out of these 10, 5 are still ongoing. Dr. Priyank has already guided more than 30 master's theses in engineering and has also supervised 4 PhD theses at Birla Institute. So welcome, Dr. Priyank. It's all yours now. Please.
Thank you so much, sir, for giving me this opportunity, and I'm really thankful to NCERT for providing me a platform so that I can interact with the students, and this is very important. So I'll be basically talking about the wind tunnels and their applications. So before I proceed, let me tell you that when we talk about a wind tunnel, in fact, if we get into some kind of fluids is going to be everywhere. If you look into our Earth's surface, we have water, we have air, so fluid, whatever you do, wherever you see, even if you are talking, right, so we have the fluids. So let me get on to my slides. So this is a typical thing which I have taken. This is what I was talking about. So we have our Earth's surface. So if you look into this particular Earth's surface, we know that as a thumb rule, 70% of this whole Earth's surface is covered by water. So that is one fluid. And then we have all over atmosphere. So that consists of a very large area. Maybe if we assume that up to 100 kilometers, if we have some kind of atmosphere, there are so many, so many mixture of gases which are over there. And in fact, if we also look apart from 100 kilometer altitude, so is it is it vacuum? Yes or no? The question is, it's not actually vacuum. It's again a fluid which has a higher intermolecular distance. So when we are talking about the atmosphere, it's a continuum fluid. So as if the fluid is continuous, but when you go outwards towards the outer atmosphere, it's not continuous. It's you call it as a free molecular flow. So nowhere there is no escape out of the fluid. So starting from biomechanics, from our eyes to aircrafts, everywhere we actually face fluids. So let me come on to some of the very typical problems which actually is seen, and some of the problems have been seen from the history itself. There are two pictures which are shown in this slide, and the very first picture, this basically is a boat which might have been utilized about 1,000 years or 2,000 years ago. So if you look into the boat, there is a particular sail which is made of cloth, and then there is a shape of boat. But then onwards, if you look into the recent time, the complete sail has a different shape, and the boat itself has a different shape, probably kind of a streamlined shape. What could be the reason? Because the reason was, initially the major aim was transportation, but if you look into today's board, there are so many things. It is being used for transportation, it is being used for wars, it is being used in sports. So there are plenty of applications of this kind of boards, and based on that, there are several changes which has been made. Whether this changes has been made of its own, no, there are some designs, engineers are actually involved over there, and some designs, modifications have been made into the sails, depending upon the requirement. Now let's look into the other slide. If you look into these vintage cars, the cars of 1900, maybe 20s or 30s, the major requirement was transportation, and then people were not bothered about that what is the kind of fuel efficiency it is going to give at that time, because the thing was it had to start. So nobody was bothered about the aerodynamics, but later on when it all started, we came to some kind of fuel efficiency, and those things started coming up, and it was actually observed that there is some kind of drag which is actually making more and more fuel consumption. So somewhere in 70s, there was some modification in the car. This is what you see in picture number 2. So that car was slightly modified, it was streamlined, and obviously the drag means the pulling, some kind of resistive force which is coming onto that body. So that particular thing was reduced. And now if you look into the third picture, which is the which is the recent cars which we have, so that is completely streamlined, right? So if we compare, if I slightly get into more detail of this, if you look into the drag values, there is a non-dimensional drag value which we call it as drag coefficient. So the CD value for the first picture might have been of the order of 0.5 or 0.6, but the CD value of the last picture is of the order of 0.1 to 0.2. That means it has been drastically reduced. And depending upon that, you are going to have more and more speeds. So the very first car might be having a maximum speed of 70 km per hour. If you look into the last car, the recent cars, that has a speed even crossing 200 kilometers per hour. So that is the difference. Who is playing the role? If you look into that, we are basically trying to reduce the air resistance. Let me come on to the third picture, which is one of the the first picture is the most important picture. The first plane which was which was actually developed by the Wright brothers. So then onwards, that's the first picture is of a bi-wing plane. If you look over there, one of the brother was sitting on the plane and the other is standing outside. So then onwards, look into the transformation of technology which has taken place. The second picture, if you look, the second picture is the conventional aircraft we had been using, the passenger aircraft. The maximum passenger size of that aircraft is of the order of roughly around 200 to 300 passengers. But now the transformation is moving towards something what we call it as a blended wing bodies, right? And we are going to have maximum volume at minimum surface area. So basically the scientists, the researchers, they are aiming towards to have a total passenger of around 700 to 800 passengers at one go. So that's the transformation in the technology. Apart from that, one most important thing is the speed. So the speed also has to be pretty high. This is another example I have taken because it's always fascinating to me. If you just believe that there is a very huge tall building and it is actually facing some kind of a gust of a wind, the wind may be of the order of 30 or 40 km per hour. What's going to happen onto the structure? Is it going to vibrate? What will happen? Now let's think of another problem. For that particular building, put another building by the side of it. What will happen onto that building and what will happen onto the previous building if there is a flow? The third case, what will happen if there are a cluster of buildings, something like the one which is shown in the picture? So if there are a cluster of buildings, obviously fluid dynamics is going to be playing a very major role. And imagine that is, I'm just talking about some kind of similar buildings. Now what will happen if you have the structures of different sizes? One may be rectangular, other one may be circular. So that way, the flow physics of the whole building or the whole area is going to be pretty different. So these are the things which becomes very, very important. And just to show you, let me show you a typical video. What happens if there is a sudden gust of wind onto a particular chimney? This is an old picture, old video which I have taken from YouTube. So if you look into this particular chimney, this chimney is going to vibrate with respect to wind. With respect to the winds, you can see that the vibration has started, and further it will vibrate more rigorously, right? So if there is this kind of rigorous vibration and if it matches with the natural frequency of the chimney, obviously there is going to be some kind of failure. So this is very, very important to understand that what exactly is happening over there, and we must get into the physics of the fluid over there. Let me show you another, one of the very, very famous engineering failure. This is the Tacoma Bridge, which was inaugurated in November 7, 1940. You know what? Just after inauguration, with a very small breeze, roughly around of the order of 30 to 40 kilometers per hour, this whole bridge collapsed. Let me show you that what exactly happened. So, at a very small gust of wind, the bridge basically started to vibrate, right? And once the vibration was higher, it actually matched with the natural frequency of the bridge. The whole bridge middle column actually collapsed. And this is why I said that this is the most famous engineering failure. Look into the video and see that how it is vibrating, how dangerous this could be, right? And ultimately, this car was stuck up in between, and if you see at the end, this is going to be, this collapsed, right? If you look into the video, the middle section of the bridge actually collapsed, right? The question was, what happened, right? And later on, it was found, I'll show you at the end of the slide, that it was found that it was aerodynamics, or it's the fluid dynamics which was responsible for that. So it's very important to go through all these things. And the point is, next thing, let me come on to the birds. One of the most famous creatures we have been looking since our childhood. If you look into this kind of birds, see, they don't have a theory, they don't know about the equation, they don't know anything of the fluid dynamics, but still they're able to fly so smoothly, they're able to maneuver so smoothly that even we humans cannot replicate that. So we are still researching that what way these things can be replicated. Another very typical creature, you know, everybody has faced this. This is a typical fly. You try to hit that and it has such a fantastic maneuvering capability that you will not be able to catch hold of that fly. The second one, the third one is the mosquito. Again, mosquito itself, it keeps on flying at a very constant speed. What kind of, you know, fluid dynamic, or what kind of wings, what are the fluctuating frequencies, what it is doing, right? Another fellow is the dragonfly. All of us might have seen in our childhood, we used to tie a small thread and then play along with the dragonfly, but you know, it's so stable that scientists are actually researching on the wings of this dragonfly. It's a kind of a corrugated wing surface which is actually going to have a very lesser drag. It basically makes the flow turbulent. I mean, this is a very detailed discussion, but later on, maybe if somebody wants, they can always get in touch with us to get the details of these things, right? So again, this has a different kind of aerodynamic capability to fly and keep itself stable. The last picture which I show you are the fishes which are actually swimming in the pond, right? Hydrodynamics. So everywhere, whatever you do, whatever you see, and you pinpoint, think of a computer, computer CPU. Inside the CPU, there are so many electronic components, and there is exhaust fan. There also you have the usage of the fluid dynamics, what with the air or the hot gas is being exhausted over there. So there also fluid dynamics plays a very, very important role. This is another example of a bullet which is shot from a gun. This bullet is going to have a velocity of around Mach 2 or Mach 3. That could be the order. What is happening? What will happen in front of a bullet if it is traveling at Mach 2? You know, Mach is basically the ratio of the flow velocity to the speed of sound, right? So if it is greater than Mach 1, we call it as a supersonic velocity. So what will happen if a body is traveling at a supersonic velocity? Then again, there are missiles, the Indian missile program, which are moving from supersonic to hypersonic programs, right? What exactly is hypersonic? I'll talk about all those things as well. In fact, the fluid dynamic applications are also there in steel industry. When you see molten metals flowing, there also you have a lot of usage of this fluid dynamics. Apart from that, you know, there are, for a basic oxygen converted in the metallurgy process, there are what you call it as a sub-entry nozzles, right? And you call it as a oxygen lance, from which the oxygen is basically impinged into the molten metal at a supersonic velocity, right? So that is again very, very important, and we need to model those things. Now this is one of the most fascinating things. You look into the sports, look into any of the circular structure over there. Let it be a basketball, volleyball, football, or maybe cricket ball or a tennis ball, everywhere you have the application of fluid dynamics, and even the space shuttles, right? Look into the people who are actually riding the bicycles. There also fluid dynamics plays a very important role. You might have noticed that in a cycle race, people actually, most of the bicyclists, they actually come down and they basically try to reduce the drag, right? One of the most famous cricketer, I have just taken his picture, Mahendra Singh Dhoni. So the question is, why I have just shown this particular picture to make you aware that the reverse swing, what the bowlers do, that is also very much dependent upon the aerodynamics of that particular ball. Again, in swimming, it is becoming very, very important, right? The point is how to analyze all these problems what I had been talking about in the past 10-15 minutes, right? The answer is the wind tunnel. So what exactly we are going to do is, in case of a wind tunnel, it's a kind of a tubular structure with some differences in the cross-section area. So at a particular cross-section area, we are going to reduce the cross-section area, and the flow velocity is going to be higher in that area with a lower pressure. This is what we see in the Venturi effect. And we try to basically find out that what are the flow velocities over there, what velocity is required at that particular point. These are the things which actually we try to find out. So let me tell you that why at all we need a wind tunnel. See, what we are going to talk about is either the body moves into a stagnant air or the air moves onto a body. We assume that it's going to be the same thing. Basically, it's the concept of the relative velocity. But when you look into more details, let me tell you that many a times we feel that it's the same thing. But you know what? There is a lot of differences which comes in between. See, when the body is moving into a stagnant air, believe me, that's a stagnant air, right? It's not moving at that point, and the body is moving in that direction, okay? But when we are trying to make the air move onto that particular velocity, onto that particular body, so in that case, we need to see that the flow is undisturbed in the front. That means I'm going to have minimum disturbances in the upstream flow. That is one of the most important requirement of a wind tunnel, right? Apart from that, there are a few things what we do. We call it as a geometric scaling, right? So we scale down the model of in a similar way. So we scale it down by 120 or 130, whatever is our requirement, and then we try to put it inside the wind tunnel. And then there is going to be something what we call it as a flow similarity, that is the dynamic similarity. So when we talk about the dynamic similarity, we talk about some non-dimensional numbers, because you know the aerodynamics engineers are very fond of talking about the non-dimensional numbers, right? So when we talk about the non-dimensional number, something like a Reynolds number, what exactly it is? So many a times when I ask my student what's a Reynolds number, they say rho Vd by mu. I say no, don't talk about the formula. Tell me what exactly is Reynolds number. So that is the inertial force to the viscous force. So one is trying to push and the other one is trying to pull. That's the ratio of the inertial force to viscous force. When you talk about a Mach number, that's inertial force to the elastic force. That's what we are trying to do. When we say that the Mach number is equivalent to the flow velocity divided by the speed of sound. No, local speed of sound, because the sound velocity is dependent upon the temperature, which is the square root of temperature. So it becomes very important that when you are doing the experiment at a very high altitude and when you are doing the experiment inside the wind tunnel, what exactly is the Mach number that we need to match. Apart from that, there are several other numbers like Froude's number, Grashoff's number. Most of the numbers are supposed to be matched. This is what we call it as a flow similarity. Now let me talk about the classification of the wind tunnel, right? Depending upon what exactly is your requirement, how much space you have, what is your economical condition, depending upon that, you basically have two different types of wind tunnel. One is the open and the other one is the closed return type wind tunnel. These two have different usage, and again, if you talk about the differences, many things are available, but one thing I can definitely say that open tunnels are quite economical than the closed return type tunnel. But again, if you need to get into more and more details and a very good analysis, closed type return tunnels are very good, right? But there are some issues of purging and all those things which definitely we can discuss at a later stage. The other one is the classification based on the speed. When I talk about the speed, there are four different regimes. One is the subsonic regime, which is less than Mach number 1. Other one is the transonic regime, which ranges from Mach number 0.8 to 1.2. The third one is the supersonic regime, which is greater than Mach 1. And the fourth one, is the hypersonic velocity, which is greater than Mach 5. Well, all have different wind tunnels. Everywhere different wind tunnels are required. And you know what? For supersonic tunnel, the structure has to be different, very robust, and for hypersonic, it has to be more robust. But that depends upon what kind of, for how much time you're going to run the tunnel, and that's again a very elaborated subject. When you talk about the applications, depending upon whatever applications you're looking for, say for example, you're looking for some kind of aeronautical application, environmental application, or building application, whatever you're looking for, these are the applications on which wind tunnels are divided. So let me first of all show you what exactly is the open return wind tunnel. So on one side, if you look into the right side of the figure, there is a typical fan which is placed, and that fan is made to rotate, and this starts sucking in the air from the left hand side of the tunnel. So this is just a tubular structure what you're seeing, and within the tubular structure, if you see, there is a convergent section, and with this convergent section the speed starts to increase because we are just trying to restrict the area of the tube. So it starts to increase, and then you have a constant test section where the speed becomes uniform. So that is the test section where we actually place our test models, whatever models are required, whatever I talked about, the geometric scaling, dynamic similarity, all those things are supposed to be taken care of within this test section. And then there is a diffuser, which is again the air is taken out of this tunnel. This is a typical subsonic tunnel of test section 2 feet by 2 feet, which is available at in the aerodynamics laboratory of BIT Mesra. These are the supersonic tunnels which are available at BIT Mesra. It's a blow down type tunnel, again an open type tunnel, and the air is made to go outside. So these are two tunnels which can reach up to around Mach 3.5 if we change the nozzle blocks. There is a closed return type tunnels. This is again this picture I have taken from NASA website. So this again is a costly affair, but here the quality of this kind of tunnel is that you're going to have very good results coming out of this kind of tunnel, right? And the noise is very less. In open type of wind tunnels, the noise is very high. So there are even if you want to do some kind of aeroacoustic testing, those can be done over here. This is a typical figure which I have taken from Google Images. That's the closed return type wind tunnel. So the question is, why open circuit and closed circuit? This is what I was talking about, that that depends upon your requirement, what you're looking for. But again, the open type is economical, and the other one is a costly affair. You need a lot of space for a closed return type wind tunnel. The space requirement for open type wind tunnel is quite smaller in comparison to that. Again, the power requirement depends upon what you're looking for, right? But the quality requirement, the kind of vanes and all which is required, that is very high in the closed return type wind tunnel. You need to have vanes. You need many a times you need to do some kind of cooling system which is to be installed in closed return type wind tunnels. So it's basically a costly affair for the researchers, right? But for university level or college level, the open return type is more suitable. Now let me come on to some of the classifications. So one classification are the high Reynolds number wind tunnels. So if I need to go for a higher Reynolds number, what shall I do? So let me get back to the same formula when I talked about rho VD, where rho stands for the density, V is the velocity, and D or L is the characteristic length by that dynamic viscosity. So what we can do is, in order to increase the higher Reynolds number, either we need to increase the velocity, or we need to increase the length, or we need to increase the density. So this is a typical variable density tunnel which is shown in this particular graph, so in this particular figure. So there are different types of wind tunnels available. Now this is again a typical variable density wind tunnel in which the researchers have put the scaled down model of a reusable launch vehicle, and they are basically going to see that what exactly will happen onto this kind of body. Now this is a vertical short takeoff and landing wind tunnel. So the basic application is they need to see that what kind of thrust is being imparted onto these bodies, like helicopters or maybe some aircrafts which are going to have a very short takeoff thing. Then there are free flight tunnels. You are supposed to hang the aircraft within the tunnel, and if required, even the tunnel inclination can be changed. So this is what we call it as a free flight tunnel. So if there is, it is just, if you see the second figure, it is the aircraft model is just suspended with the help of a typical wire. and it is being observed, experiments are being done just to see that what is happening onto this kind of body if it is in a free flight condition. Otherwise, what we do is, as a conventional practice, we basically mount it with a force sting balance and all. So something like a cantilever beam, we insert the force balances within the aircraft and try to see. So this is a typical free flight tunnel. So the aircraft is free to be there within the tunnel. Then there are problem of stalls, stalling of the aircraft when the lift suddenly decreases, right? So for these stalls, or maybe for some kind of skydiving, or maybe some kind of parachute applications, vertical tunnels are being used. You can see in picture number 2, there are some skydivers which are on which experiments are being performed to see that what will happen onto their body if they're diving into from the top of an aircraft or those things. Then we have a propeller tunnel where basically we mount the complete model of the aircraft within the tunnel, and then we try to see that what will happen if the propellers are running. So what way things are basically happening over there. Then there are propulsion tunnels where we actually need to see that what exactly is happening onto the aircraft along with the propulsion system, that is the jet engine, or if you want to look into the engine nacelles where it is to be kept, and all those things can be seen over there. Icing tunnels, this is one of the very important thing which is not available at several places, but yes, it is available probably in NASA Langley Research Laboratories. It is there. So the thing is, you're supposed to put up the model, and then there is an option of reducing the temperature up to -40°F, and the icing takes place. What will happen if these things are there? What will happen onto the body? Because there are several conditions, somewhere in Siberia or somewhere, that these things are being experienced. So again, this is what has to be seen. There are two-dimensional tunnels which basically we actually restrict one of the sides of one of the dimension of the wind tunnel, and we try to see that what exactly is happening in that case. So you can see that there are some smoke, which is some smoke linings which are being fed onto the body, and we're just trying to see that what is happening, what way the flow is adapting itself according to the body. Then there are automobile wind tunnels. Again, one of the most important thing in an automobile wind tunnel. See, the point is, we need to understand the difference between the aeronautical tunnel and the automobile tunnel, because one of the most important thing is that we need to look into the ground effect, and basically the bottom of the wind tunnel is expected to have similar velocity with which your body is running, so that the boundary layer which is developed, because if you have a stationary flat wall, you'll have a boundary layer which will be developed, and that may affect the aerodynamic characteristic of the vehicle. So we need to have a moving surface of the wind tunnel. That is what is one of the most important requirement, and that is what is observed in some of the tests which is being performed over here. You can see the pictures. Again, the ground effect is one of the most important thing which is supposed to be taken care of. Imagine that you have a very, very high, the distance of your ground clearance, what we say. Right, so if you have a very high ground clearance of a vehicle, and the vehicle is supposed to move at a very high speed, what will happen? It will just act like an aerofoil, and you'll have some kind of lift which will be developed. So you can have some kind of movement which may try to topple that particular vehicle. So that needs to be understood. Again, one of the news what I saw, that Ford has invested around $200 million of US for establishing its wind tunnel for the automobile testing. So people are investing a lot. There are climatic wind tunnels. If we have some kind of fog, what will happen onto the body, right? What way it is affecting the characteristic of the body? These are again similar things. What will happen if you are moving in a rain, right? So if you have rain, again these things have to be taken care of, right? The testing are supposed to be done. There are aeroacoustic tunnels when we try to see that what kind of noise is being generated due to the pressures, right? These are very special tunnels which are, this is a very robust tunnel, and you need another anechoic chamber for that, through which the sound of outside cannot be acquired inside. That's what is very important. So there should be only the specific sound which is coming out because of the flow, and this is a typical anechoic facility which is there in our aerodynamics laboratory of VIT Mesra. So you can see from inside, this is what is anechoic chamber. Then there are water tunnels. So again, the testing can be done on a water tunnel. Apart from that, there are general purpose wind tunnels, say for example for peoples. I mean, peoples are like something like cycling, or there are plenty of other sports. There are tunnels for birds and insects, wind powered devices. You can think of a typical, what you say that, maybe something like wind turbines or something like that. Then you have solar panels, radars, antennas, even the dish TVs which are actually mounted onto the rooftop. They actually face a lot of wind problems, and there can be cracks which will be developed. So there also you require this kind of wind tunnel testing. Sails, bridges, sports, and several others which I had been talking about. There are environmental wind tunnels where if you need to simulate the whole city condition, if you want to simulate the flow within a particular city, that also could be done, right? What will happen if there is this kind of city, you have multiple buildings, what will be the flow physics onto this particular area? These things also can be visualized using a wind tunnels. So some of the typical type of investigation, we basically divide the investigation in two parts. One is qualitative and the other one is quantitative. When we talk about qualitative, we should be able to see something through our naked eyes, and we should be able to understand that this is what is happening, this is the kind of flow which is happening onto the body. When you are looking into quantitative, we are basically looking for some kind of measurement. Say for example, measurement of pressures, measurement of forces. So if you look into the qualitative visualization, these are flow visualization which is done by some kind of oil flow technique. There is a typical tuft flow, very crude mechanism, tuft flow technique. We place small woolen tufts and try to see that how these tufts are adapting itself according to the flow. We have mini tuft flow visualization. We have one more visualization, what we call it as a Schlieren photography, which actually changes in the density can be captured with the help of those kind of photography. Then you have the quantitative measurements, what I talked about, the measurement of forces, moments, pressure, unsteady velocities, all those things can be done. And there are some new techniques which have come up in the past 2-3 decades, like particle image velocimetry, we call it as PIV, pressure sensitive paints. We coat the model with a typical chemical compound, and once if you start the tunnel, this is mainly for the high speed tunnels. When you start the tunnels, they basically try the paints basically try to adapt itself according to the flow, and there are some changes in the colors which can be observed. There is hot wire anemometer technique, which is quite old but very good technique to get all these details. Some of the flow visualization techniques which I have taken from NASA's website are the laser sheet. So you put a laser sheet onto on the surface of the aircraft, on the cross section of the aircraft, and try to see that how these flows are adapting onto the body. Then you can see that some oil dots are sprayed onto the body, and what way these oil dots are adapting itself. Then you have the Schlieren photography, which is observed over there, which I said that it's a typical optical technique which is being utilized to see the changes in the density. And then you have several smoke and tuft flow visualization. This is again a smoke flow visualization, which I already showed you this. Now this is a laser sheet which has been kept in the cross section of a particular body, and we are trying to see that what way the flow is adapting itself according to the flow. This is a tuft flow visualization which I took from NAL website, and these you can see that there are some tufts, woolen tufts, small woolen tufts which are placed onto the wing model. And if your wing is at around 10-degree angle of attack, what way these tufts are changing, and what will happen if it has a 14-degree angle of attack. So you can see the differences, which basically represents that at a very higher angle of attack, your flow no longer remains attached, it gets separated, and you'll have a stall over there, so your lift is going to reduce. Similar tuft flow visualization is also done on automobile models. This is a typical oil flow visualization which has been done on a protrusion kind of stuff. So what you do is, even if you look into the rockets, they have very small rivets, or they have very small sensors which are protruding outside. So what will happen if it experiences a supersonic flow? So we spray oil dots onto the surface of the body, and we just try to see that what is happening. Then again, similar laser flow visualization, and we do something using your computational fluid dynamics. So we solve the equation and try to see that what way flow is going to behave. And again, you can see that this is a typical oil flow which has been done on a typical missile models. These are some of the results on delta wings, on reusable launch vehicles, and again some jets. Maybe some more oil flow and Schlieren photography pictures are there. It will be much better when I show you this video, which has been done in our own laboratory, that a blunt body is actually facing a supersonic flow of Mach 2. So with your naked eyes, you won't be able to see that what kind of shock wave is coming out over there. But with this typical Schlieren photography, we are able to see that what happens in front of this body. And if you see, the tunnel is going to start, and all of a sudden you'll see a bow shock which has come up onto this, and this bow shock is going to be very, very strong, and it's going to put up a very large drag onto this body. So in order to reduce the drag on this body, what is being done is we actually place a typical spike in front of it, and you see that the whole bow shock is now actually seen as an oblique shock in this body. So if any more details are required, you can always get in touch with me. I'll give you more details about it. But this picture clearly shows that the bow shock has transformed into an oblique shock with the help of a spike. Let me show you a typical free jet Schlieren photography, which you can see that the Mach disk, we call this as a Mach disk, something like exhaust of a rocket, what way things are going to behave. So this is what you see if I have a free jet kind of visualization over here, Schlieren photography of a free jet. Now CFD is again a very important part of today's fluid dynamic application. We call it as a computational fluid dynamics, but you have to be very, very careful when you are trying to simulate any kind of this kind of computational fluid dynamic simulations, because you basically need to compare it with the realistic cases. So I was talking in one of the slides, I was talking about the buildings. So if I just put one building, two buildings side by side, let's say. So I have just done the two-dimensional simulation of what is happening onto the floor. This is what you can see, right? So you can see the vibration or the differences in the pressures or differences in the velocity is going to change the pressures around this body, and what way it is affecting the body in the downstream. That is very important, right? Again, the next picture, if you see, this is the blunt body with spike, and something like this is what we saw in the previous slide of the Schlieren photography. So you can see that there is an oblique shock which has been developed over here, and this portion, the frontal portion, represents the spike, and the hemispherical portion represents the blunted body which we saw just now in Schlieren photography. Let me show you the another typical comparison which was done by ANSYS for the Tacoma bridge failure. So if you look over here, this was the Tacoma bridge which actually failed, and when the simulation was done, this is what was seen. So again, computational fluid dynamics plays a very, very important role in actually comparing this data and in getting the more details of the fluid flow, right? So this is what has happened, and if you look at different cross sections, this basically made the bridge to vibrate, right? So based on these analysis, I can definitely say that for any kind of, maybe if you're trying to come up with some kind of constructions for those things, it is very important to do the testings beforehand so that your bodies or the structures are not disturbed because of the fluid flow problem. Even the automobiles, it is one of the requirements in India these days that this is not much seen in India. So I definitely would refer the automobile research that they should look more into the automobile aerodynamics. Apart from that, we had been talking about what we said, that there is a failure because of the vortex shedding. So definitely I said that it actually leads to the failure. But the vortex blade people, they are basically developing some kind of bladeless wind turbines, and they are actually trying to harness energy from the vortex induced vibration itself. Right, so they have actually placed some kind of alternators, and there is some way they are trying to find out. And if you look into this video, if you look into this video, this itself shows there is some issues. Anyway, so you can just look into this video. It itself will show that what way it is vibrating, what way the turbine is vibrating, and it is trying to get the power out of it. So it can also be used in a constructive way. Thank you very much.
It was a wonderful presentation, sir. We learned a lot of things regarding the wind tunnels and how they're used for different purposes. And there are so many types of wind tunnels that are used entirely in the industry, be it automobile industry or other industries. So you showed in one of the pictures there were construction sites where you said that they need to be checked before getting into use. So the fluid needs to be checked. Here we have a live example of Noida Twin Towers. Everyone has heard the news. So they are being demolished, and the news says that it's unsafe for people. So is there any wind tunnel error in their construction error that's related to our subject today?
See, probably it's not very common in India that people do building aerodynamics. There is a very limited cases which is being done in India. So definitely, I'm really not very sure about that, but definitely that could play a major role, because if you have those very high twin tower structures, there could be some issues of fluid dynamics. There could be some problems. So definitely.
So Dr. Priyank, it was wonderful listening to you indeed. But coming forward with what Tanvi has made a point of interest today, because this Noida Twin Tower destruction is in news nowadays. It is going to take place on Sunday, August 28th. There are many questions related to it at this moment. See, can we study? You mentioned about computational fluid dynamics techniques, and you specifically took the case of two towers together, and in one tower something is happening, what effect is going to be happen in second tower, and so far so on. So now the curiosity is, there are so many questions which are arising into the individual's mind, particularly those who are residing in that area, that will it lead to earthquake, will it lead to some wind turmoil, some turbulence, wind turbulence, which obviously we think naturally also. But the curiosity in this backdrop is, can we really see or model these kind of studies in our wind tunnels?
Definitely these things can be modeled. In fact, I had been talking since a long time. I mean, I have even talked to several civil engineers and other people as well, that it should be made mandatory that the wind tunnel testing of the building should be there, right? In fact, if you are going for such a high-rise building within an area, it becomes very, very important. See, because there can be pocket of winds or pocket of vortices which may affect the other buildings in the surrounding, right? So, in my opinion, it's very important. This is what
the point of interest at this time to do all those. I also live around that place, so this is the very curiosity. Then there are some natural questions. Yes, you mentioned. Yes, you repeatedly said nature, bringing from the nature and looking at the nature, and then how the birds are flying and how the natural exercise takes place.
Yes.
So in fact, while listening to you, I was seeing a strange and very good mixture of science, engineering and technology, all three together, which is very unique in your session today. Now, see, coming back with this kind of similar example, you took the example of 2 feet by 2 feet test. Can we come to your slide number 14 and 15 or so?
Sure.
14 and 15.
Probably somewhere here, sir.
No, 14 and 15. No, regarding this.
15.
Yes, this. No, I mean the slide just above it.
Yeah.
This slide which you're showing. Please bring it on the display mode. Yes, that's okay. Okay. So now you took the example of a test center, 2 feet by 2 feet.
Yeah.
And in the next slide to it, you showed the tunnel at BIT Mesra.
Yes.
Can you correlate that particular 2 feet by 2 feet in this diagram? Please use the arrow around it.
So 2 feet by 2 feet is the height of this, and the width of the wind tunnel.
And how about the length?
Length is of the order of around 1.5 meters or so.
So roughly 7 meters, roughly 6 meters or so. 6 feet.
6 feet, yeah.
Roughly 6 feet.
Around that.
So now this is such a simple, such a small, not very large kind of test centers. When you talked about dynamic similarities.
Yes.
So when you scale down the buildings and the phenomena or the vehicles, then we see the reflect actions from the boundaries, which you said that the closed boundaries are going to have probably even more than that what you are going to have in open systems, open tunnels. So how to handle all those things and how to descale all those things so that one can realize the true picture of it.
Yes. So basically, when you talk about this kind of open circuit wind tunnels or closed circuit, the basic idea is we are going to have some kind of uniform velocity within the test section.
This is what the definition of test center.
Test section, that is uniform velocity is required over there. Now, when you are trying to reduce, as a thumb rule, what we do is we try to keep the blockage ratio, that is the kind of models we are keeping inside the test section. So the blockage is basically the area of your body to the area of your whole test section. So the blockage ratio as a thumb rule should be less than 5%, so that we are in a free zone. This is what, and the tunnel is, I mean, the flow is not disturbed because of the wall effects.
So roughly a scaling, considering this 5% scaling factor, what are the roughly dimensions of the wind tunnels? Suppose if I want to check an e-rickshaw, for example, its size is roughly say 6 feet by 5 feet, and height is roughly again by 6 feet or so. Now this kind of a structure, wind structure, speed is not going to be more than say 30 kilometers per hour or so. Around, in any case, it is not expected to be more than 40 kilometers per hour. It's in the sonic region. It's in the subsonic region, in fact, subsonic region.
Low subsonic,
yes, very low subsonic region. So what kind of wind tunnel we can think of just for our mental picture?
Yes, sir.
What should be the size of the wind tunnels? Minimum?
So the size of any wind tunnel could be made. That depends upon whether
looking into this 5% factor.
Any kind of wind tunnel can be utilized for this. But see, what we'll do is, if you are looking from 30 kilometer perspective, 30 kilometer per hour perspective, our wind tunnel can go up to 30 meter per second. So that's quite a high velocity.
Quite very high, very high.
Now we need to match our Reynolds number. So if it can come down to that particular Reynolds number, any model, I mean, that depends upon, it should be fairly large to the extent possible. We can have at least 1:20 scale of that, or at least 1:15 to 20 scale will be good.
That's I mean,
so
the
we need
question,
to scale down the model.
Priyank, the question comes into our mind, into the individual's mind, is looking into the newspapers every day, and whenever we have a new airport and new building around it, let me recall, because we live in this city, we have a runway in Indira Gandhi International Airport.
Yes.
The pathway of runway is coming from above the Shiv Murti therein.
Yes.
And the height of Shiv Murti was advised to be reduced because it was affecting. What was happening that when the aircraft is moving, it puts the air pressure downwards, and it is reflected back by the structures below.
Yes.
And this is probably the reason. This is probably the only reason why we can't have many high-rise buildings near the airports.
Yes,
so I mean, this. If you look at these scales, it is still, though you have tried to make me to understand, it is still little difficult to imagine.
Yes, sir.
The scaling sizes. So, though the 10% you have given 5 number,
so that
10
is
to 15%.
that is just for wind tunnel modeling. So now, if you are just trying to find out, if we need to figure out that what is going to happen in a city, so we need to create that particular model within our wind tunnel test section. So again, that scaling factor has to be taken care of.
How much it is roughly? In many cases, I have heard this is around 100% or so.
Regarding
this scaling factors. I mean this.
So it is the best thing would be if I go for the actual scaling. But again, it's not possible because we cannot have that kind of tunnel, and the cost required will be very huge. So definitely we need to compromise somewhere. So this is where the dynamic similarity plays a major role.
Okay. Then how high you started with the atmosphere? You started with the aerodynamics in the Earth's atmosphere itself.
Yeah.
So our aircraft, the civil aircraft, fly nearly say 10 kilometers above the surface.
38,000.
Roughly 40,000 feet or so.
Yes.
12 kilometers or so. And these defense aircraft fly even more higher,
yes, sir.
Sometimes more higher. This atmosphere height is considered to be 100 kilometers, roughly. Where we put our satellites, normal satellites, though the geostationary satellites are even higher. Going back from this level to higher level, I mean, the kind of aerodynamic conditions which are around the surface of the Earth are quite different from the kind of aerodynamic structures, not only aerodynamic but the thermal properties as well, which you mentioned.
Yes.
The temperatures around minus 40 degrees centigrade temperatures and etc. etc. Now the kind of materials which we may require to handle such a diverse conditions are to be different.
Yes.
Can you suggest us some, for example, the one is of that kind of carbon fiber materials, something like that,
Yes.
aluminum magnesium alloys. I mean, aluminum magnesium alloys are often used in these aircraft.
So to be very frank, I'm not much into the structures, but just like you, I mean, yeah, alloy material could be, it has better strength over there.
Yes.
So I mainly look towards the aerodynamic perspective.
That's great. That's great. I can understand. Yes, I can understand all these things. And there are some more. There are some more questions, some more ideas to behind it. You talked about the critical drag value. It was a little difficult to comprehend. Can you please?
Was it
speak
related
little
to
more?
the automobiles?
Automobiles? Yes.
Oh yes. So in that particular case, let me get back to the slides because
Please,
I always love to talk about this.
Yes. Yes.
Yeah, this was the slide I was talking about.
Yes,
So in this particular slide, this value at this particular moment, people were not so much bothered about what is going to happen onto the aerodynamics. Because the most important thing was the body should be able to move, right? So the drag was mainly coming out either from the wheels or from the this grill which is over there. So there were plenty, and if it is a open kind of stuff, or it's like a bluff body which is in a flow. So now if the wake is very large, if the wake region, I mean downstream of the body, if the wake is very large, your drag becomes very high. So because of that, the CD value, the drag coefficient value was larger for this kind of vehicles, but later on it was actually streamlined. So now if it is streamlined, something like just like an aerofoil, right? So if it was streamlined, the drag value is reduced. And if you look into this kind of Mercedes-Benz or Porsche
or
car,
Ferrari,
it is similar to the aerofoil.
Aerofoils, yes, this is what. So देखिए प्रियांक साहब, सपने देखना, हम साइंस के स्टूडेंट हैं, सपने देखना हमारा काम है और हमें ट्रेनिंग दी जाती है कि हम सपने देखें. सो एज यू डेफिनेटली कितना स्पीड हम एक्सपेक्ट कर सकते हैं कि रोड ट्रांसपोर्ट पर कितना मैक्सिमम स्पीड डिस्पाइट ऑफ ऑल दोज फैक्टर्स कितना स्पीड हमको मिल सकती है प्रेजेंट टेक्नोलॉजी के हिसाब से?
सो प्रेजेंट टेक्नोलॉजी, आई मीन इफ यू गो बाय दिस काइंड ऑफ पावर्ड इंजन्स, तो मेरे ख्याल से अराउंड 300-400 किलोमीटर पर आवर पे तो
फरारी स्टिल ऑलरेडी 350
हाँ, तो वो मिल सकते हैं. बट हमारे रोड कंडीशंस और देयर आर सेवरल फैक्टर्स अपार्ट फ्रॉम दिस. So
formula races can be
keeping in view safety, even safety of the young ones especially.
But probably I particularly feel when we start using good thermal materials, because it's not only the mechanical properties of the materials, it has the thermal properties as well. We can go even higher. The bullet trains are even
bullet trains सर. इनफैक्ट आपने हाइपर लूप भी आजकल काफी बात चल रही है. इनफैक्ट आपने ये भी देखा होगा, अगर कभी डिस्कवरी चैनल पे देखे होंगे तो रॉकेट पावर्ड व्हीकल्स वहाँ पे काफी लोगों ने यूज किया है. दे हैव वेंट टू अ वेरी लार्ज, वेरी हाई स्पीड, 800 किलोमीटर. उस ऑर्डर में भी वो लोग गए हैं,
इस ऑर्डर तक जा चुके हैं.
बट अगेन हाउ सेफ इट इज, दैट्स वेरी डेंजरस.
That's
safety is one of the most important.
Yes, initially we all students of science go for ideal kind of situation, and then slowly we come down
depending upon the conditions.
We scale them down. So it was indeed nice talking to you, Dr. Priyank, today. We are lucky enough to have you here in our studios today. We still have so many questions with us, but now we are running slightly short of time.
Absolutely.
So Tanvi, before we wind up, want to say something?
Yes.
Yes.
So, sir, it was indeed very interesting session, and the best part I found was that icing tunnel you mentioned, it's used by NASA. It's a very rare thing, and I don't think most people know about it. I'm one of them. Now I know, and I'm going to research further about it. So thank you so much, sir, for this information which we were not aware of, and now we know. So this knowledge is precious actually. Thank you so much for being with us and sharing all these details with our viewers and with us. Thank you, and thank you so much, Gagan sir. Yes sir, but before leaving we have to announce what are we going to bring on our next session. That will be on next Friday, which is 9th of September. So let's ask Dr. Gagan Gupta, what is it all about?
So friends, India is having a lot of challenges as far as power industry is concerned. You are seeing electric vehicles, you are seeing electric batteries, new batteries, Mostly we have new batteries in telephones, in mobile phones, etc. Everywhere. We are presently using lithium-ion batteries. Now, there are changes, there are many challenges in this area too, where we can have more and more power stored in our battery systems, and so that the price of these batteries may come down and their efficiency increases. So next, on 9th of September, we have Professor Veni Madhav Adhyam from the Cryogenic Engineering Center of Indian Institute of Technology, Kharagpur, who is pioneer in working in this battery manufacturing in this country. So he will be explaining us about all those battery structures together with the new avenues in this battery manufacturing. Probably some down, as I said while talking to Dr. Priyank today, that और मैं हमेशा कहता हूँ कि सपने देखना हमारा काम है. हम साइंस के स्टूडेंट हैं, साइंस के विद्यार्थी हैं, टेक्नोलॉजी के साथ लगाते हैं. तो हो सकता है कि कल थोड़े दिनों बाद इन प्लेस ऑफ द lithium ion batteries can we use sodium ion batteries, which will be quite cheap and maybe more efficient as compared to helium ion batteries or lithium ion batteries. So thank you very much, and looking forward meeting you again on 9th of September. Thank you, Tanvi ji, and thank you Priyank once again.
Thank you, sir,
for being with us.
Absolutely. Thank you. Thank you so much to all the viewers once again for being a part of this program. And like Sir said, battery manufacturing in India, that would be our next topic. So I'm sure you all science students, science lovers and our dreamers, you will be looking forward to this session just the way we do. Thank you so much. Take great care of yourself and namaste.